Good morning, all you positive people. We're going to start chapter 6, differential equations. We've seen a few of these before, but the idea in this chapter is we're going to study one of the most important applications of calculus, which is called differential equations. We're going to really learn one method of solving these types of differential equations, and then we're going to apply these methods to solve some problems involving differential equations. But whenever you say like when is like derivatives and integrals actually used for in the real world, differential equations is a topic that does a lot of it, and there's a lot of I mean it's just one chapter in this book, but you can study that, you can major in that, and there's a lot of different avenues through differential equations. So there's a lot going on here, and we're only going to see just a little bit of it. Um, we're just going to kind of introduce the idea of this chapter. There's not going to be much to do there. And then after that, we're going to do in 6.2, look at exponential functions, growth and decay, which is going to be kind of a review of some stuff you've done in Algebra 2. But it's good if you're not familiar with exponential, like that E and ln. It'll be a good review of that. We're going to use a separation of variables technique to solve differential equations, which you're going to see today. Or excuse me, probably going to see next time. Um, and then the whole point the main reason I want to get into this chapter is because I want to look at something called the logistic equation, which models population growth, which can also model stuff like disease spread. And so, like a lot of graphs on TV during COVID involve the logistic model, which is kind of neat. Anyway, so the beginning of this, we're just going to talk a little bit about the idea of differential equations. We'll do a quick couple examples, then your homework is going to, or in class, we'll do some problems using that are similar to the examples I'm doing in the video. But in 6.1, I just want to be able to define a differential equation and how to check if we have a solution or not. So in this text, we're going to learn that physical phenomena can be described by differential equations, and this is what a differential equation is. So if you have your notes up, this is what you want to write down. A differential equation in x and y is an equation that involves x, it involves y, and the derivatives of y. It could involve the second derivative. It can involve the third derivative. If it just involves the first derivative, we call that a first order differential equation. If it involves a second derivative, it's a second order differential equation, and so on. And then next class, we're going to, in section 6.2, we're going to do some problems involving radioactive decay, population growth, and Newton's law of cooling. So this will be next time. So a differential equation is an equation that involves x, y, and its derivative, and we call y equals f of x a solution to the differential equation if the equation is satisfied when y and its derivatives are replaced by f of x and its derivatives. That's something that we can write down, but let's look at an example as well just to get a better illustration of what's going on here. So for example, differentiation and substitution would show that if I take y to be the function e to the negative 2x, that will be a solution of this differential equation right here. The derivative of y plus 2 times y equals 0. So down here we have a differential equation because we have an equation of y's derivative in y, and allegedly this is a solution to it. So what I'm going to do is I'm going to take the derivative of this, plug it into y prime, and plug e to the negative 2x in for y and show that that's going to give you 0. So you can copy this down in your notes. We're basically show y is a solution. To this differential equation. And we're given what y is. So if I know y is e to the negative 2x, we find the derivative, which is going to be e to the negative 2x times the derivative of that negative 2x, which is negative 2. So what we need to do now is check that if I plug that in for y prime. So if I replace this equation, y prime plus 2y, y prime we just said is e to the negative 2x times negative 2, which is just negative 2 e to the negative 2x. Plus 2 times y, and y we are given is e to the negative 2x. This should be 0. And maybe if you don't see it yet, this is just negative 2e to the negative 2x plus 2e to the negative 2x. Those do cancel out, and we do get 0. So it does turn out that this equation y is indeed a solution to the differential equation. The derivative of y plus double y is 0. That is one particular solution. In general, I could have had any constant in front of that e to the negative 2x, and it still would have worked out. So that's what we call a general solution, where c can be any value, any real number. So that's what it says down here. Y equals c times e to the negative 2x, where c is any real number. This is a solution. This solution is called the general solution. Some differential equations have singular solutions that cannot be written as special cases of the general solution. However, such solutions are not considered in this text, so we won't see things that nasty. We actually did a second order differential equations in the beginning of chapter 4. The order of a differential equation is determined by the highest order derivative in the equation. So the derivative of y equals 4y, that's a first order derivative. So we have a first order differential equation. First order linear differential equations are going to be discussed in 6.5. But back in 5.1, back in chapter 5, example 8, we saw that the second order differential equation to this differential equation, the second derivative is equal to negative 32t, has this general solution. And if you think back to the Smurf packet, that's the equation that we used back in 5.1. We're given that the acceleration is negative 32. We took the antiderivative of that to find the velocity, negative 32t plus some constant. We ended up finding out that constant was 64 in this case because of the initial conditions. And then we took the antiderivative of velocity to give us the height equation, which is the solution to that second order differential equation. We used the initial condition to find out the value of the constant, and we got this height equation. But we did solve a second order differential equation, except they just called this C1 and C2 in this example over here. Anyways, so here's some examples, and this is what you're certainly going to want to copy down. Determine whether the function is a solution to the differential equation, the second derivative of y minus y equals 0. So there's 4 examples here, and we're going to see if there are solutions or not. And this is what, by the end of this lesson, hopefully that's what we can do is we can check if we have a solution or not. So if I want to check if the equation y equals sine x is a solution to the second derivative of y minus y is 0, it means to find out what the second derivative of this is first. So I can substitute in for y prime. We're going to substitute sine x in for y and see if they cancel out. So the derivative is green. The derivative of sine is cosine. And then the second derivative is red. The second derivative is going to be the derivative of cosine, which is negative sine. So let's check if that really is a solution to the differential equation. The second derivative minus y, we hope is 0. The second derivative is going to be negative sine x. And if I subtract that from y, which is sine x, so I'm just substituting the second derivative in for y prime and the original function in for y. And, there's a double negative here. So we have minus sine x, which is minus 2 sine x. So this is not equal to 0, so it is not a solution. So that does not equal 0. They did not cancel out. Okay, so not a solution. Let's see if y equals 4e to the negative x is a solution. Well, I need to find out the second derivative so I can plug it into the differential equation. So the first derivative of 4e to the negative x is 4e to the negative x times the derivative of negative x, which is negative 1. So that's negative 4e to the negative x. Now for the second derivative, We just take the derivative of that. The derivative of negative 4e to the negative x is going to be negative 4e to the negative x times the derivative of negative x, which is negative 1, which becomes positive 4e to the negative x. So if I substitute that into this equation, do I get 0? Well, the second derivative of y is 4e to the negative x. And minus y, we know y is 4e to the negative x. Yeah, this is going to cancel out 4e to something minus 4e to that same something is 0. So yes, we do have a solution. So B is a solution to that differential equation given. Let's try C. Take the derivative of C e to the x actually is C e to the x. Piece of cake. The second derivative is going to be the same thing. So if I replace the differential equation, the second derivative minus the original function, do I get 0? So the second derivative is C e to the x. The original equation y is C e to the x, which they do cancel out. So that also is a solution. And then this last one, y equals x cubed. I just added this one in for fun. Is that a solution? Well, the derivative is 3x squared, and the second derivative is 6x. So if I take the second derivative minus the original function, that's the same thing as taking 6x minus x cubed. Nothing crosses out, so that is a no. That's not a solution. So that's example 1. That's how we check if there's a solution. Whatever the differential equation is, figure out what the derivatives are, figure out what the original function is, which is going to be given, plug it in, and see if we do get this value that it's supposed to be equal to. Okay, so same example, but different function to check. So take a minute to copy this example down. Determine whether the function is a solution to the differential equation. So x times y prime minus 2y equals x cubed e to the x. This is the differential equation right here, which I will call a DE. I'm going to plug y in for this y right here. And I'm going to find out what y prime is and plug it in here. So let's find out what the derivative is. So the derivative of x squared e to the x, this right here, I'm going to need to do a product rule. That's the fg prime plus f prime g to take the derivative of that part. So the fg prime means leave the first function, which is x squared alone, and take the derivative of the second one. And the derivative of e to the x is just e to the x, so that wasn't bad. Plus, now take the derivative of the first function, x squared, which the derivative of that is 2x, times g, which is the second function. We're just going to leave that alone. So that's the derivative of that green part. And then minus the derivative of 5x squared is just 10x. So that one was just an easy polynomial. Okay, so I'm going to plug that into y prime now. So if I take my differential equation, x times y prime minus 2y, hopefully I get this thing to equal x cubed e to the x. If not, then it's not a solution. So if I take x and multiply it by the derivative of y, that's the same thing as multiplying it by x squared e to the x plus 2x e to the x minus 2 times y, which we know y from right here is x squared e to the x minus 5x squared. So I want this to simplify to x cubed minus times e to the x. Let's see what happens. If I distribute the I missed the minus 10x. If I distribute the x in here, I'm going to get x cubed e to the x plus 2x squared e to the x minus 10x squared. And then if I distribute this 2 in here, we're going to have a negative 2x squared e to the x and a plus 10x squared. So right off the bat, this negative 10x squared and that 10x squared do eliminate each other, which is nice. Are there any like terms? Let's see, I have a 2x squared e to the x minus 2x squared e to the x. Those are also going to eliminate each other. And so I'm just left with x cubed e to the x. And that is what I wanted it to be. So therefore, this is a solution. So yes, we determine whether the function is a solution. Yes, it is. All right, and then the last part of the homework is just solve these differential equations by integrating. So this is gonna really just be a review. Um, to find out what the original equation y is, we're just going to integrate. Before that, I want to make sure all my x's are together and all my y's are together. So in this first example, I can just multiply both sides by dx times dx. So we have dy is 6x squared dx. And then what I can do to both sides to solve for y is to undo the derivative of y, just integrate both sides. The antiderivative of dy is just going to be y. You can think of it as like the antiderivative of 1 is 1y. And the antiderivative of 6x squared dx, so that's going to be 6x to the third over 3. Now, I could have put a plus c on both sides, but I can just subtract, c1 and c2. I could just subtract this constant on both sides, and the constants would be like terms, and in the end, you would just have some constant. So we don't need to do a plus c on both sides. So 6 over this, I mean 2x cubed plus some constant. And that would be the general solution to that differential equation. This next one here, do the same thing. We're going to multiply both sides by dx to get the x's on one side. So dy is just x times 1 plus x squared dx. We'll integrate both sides. So the antiderivative of dy is just y. And this integral is going to be a little tricky here. We have a quotient, and I can't do anything to simplify the quotient. But what I am seeing is that denominator is 1 plus x squared, which the derivative of 1 plus x squared is 2x, and I see this x up here. So I think I'm going to be able to use u substitution for this integral right here. So if I take u to be 1 plus x squared, the derivative would just be 2x dx. Now I don't need that 2, so I can just divide both sides by 2. So half of du is x dx. So I'm going to first rewrite this integral as 1 over 1 plus x squared. I'm going to move that x next to the dx. And if I do the substitution, this is 1 over u. And then the x dx is just half of du. So the antiderivative of that, the derivative of 1 over u is going to be the natural log of the absolute value of u times 1/2 plus some constant. And the function is 1 plus x squared plus c. And I took out the absolute value just because I happen to know that 1 plus x squared is always going to be a positive no matter what, because x squared is going to be 0 or bigger plus 1. So this will never be negative, so I don't need to take the absolute value of it. And there's the general solution. Okay, and that's it for this section. I'm sorry it was a little wordy. The main thing for you to get here, at least example-wise, is these examples right here. Can I verify whether I have a solution or not? And can I solve a differential equation just by integrating? And that's it.